Friends, today we shall be discussing on the computation of uniform flow. In the last class we could see what uniform flow is, and of course we could see that how the resistance flow formula we could derive, or rather it is an empirical relation with some analytical base. So, how we could get those formula, and today we see by using those formula how we can compute the required parameter of uniform flow. Well, just to recapitulate what we did in the last class, let us see that we studied development of uniform flow. Well, that means there we did discuss that we need some before developing the uniform flow, or before the uniform flow gets developed, some portion there may be transition, and then gradually it is coming to a uniform flow pattern. In a channel, when there is some changes, then the flow get disturbed again, and then again when there is a long reach having without any change, and then normally we get that uniform flow, and that depth of flow we referred as normal depth. Well, then of course we did discuss about resistance flow formula, and there we could see that several uniform flow formula have been developed, and in different part of the world people have used different formula, and out of that we can say that Manning's formula is more widely used. Of course, the Chase's formula is also used, but Manning's formula is more widely used, and some of the formula like Gangulet and Cutter's formula, that is used in channel design also. Like that, this formula could find its own application in different areas, and of course here I am just mentioning about one formula, that is Trixler formula in Europe. In Europe, a similar formula, that is say V is equal to, all this formula try to relate that velocity, try to find one expression of velocity, that is velocity is equal to some other parameter. Okay, this velocity is equal to Ks, another coefficient Ks, then r to the power 2 by 3 and Sf to the power half. Well, that formula is called Strickler formula, and as you can see that this formula is just similar to the Manning's formula. If I write here that V is equal to 1 by n r to the power 2 by 3 Sf to the power half, then you can see this is nothing but this Ks is equal to 1 by n. Of course, the value of Ks, again different people worked on this value of Ks, like Jaeger is one person who worked on that, and then he gave some relationship for finding this Ks. That way different people worked in different line. And here one point I want to again re-emphasize, that in this formula of velocity we are using here Sf. In fact, the formula is including the value of friction slope, and we remember what we mean by friction slope, or the slope of the energy grade line. Just if we somehow have forgotten that, just to mention about that, if this is the bed and if this is the depth of flow, if this, I am not drawing a uniform flow, say if this is the depth of flow, say it may be changing, then here we get depth of flow, then we get total V square by twice G energy. Of course, the alpha can be there, now we know about that, and then here suppose V2 square by twice G, and then it is Y2, this is Y1, then there may be some Z value, here it is Z1, Z2, like that. That means this point is stating about the total energy, and we are writing in the form of energy head, and the line joining these points of different energy level at different point, we got this slope as energy slope or friction slope, or we write this as a Sf. Well, now in non-uniform flow, as the velocity will change and depth will change, so this Sf and this angle we can write as Sb, bed slope. So this Sf and Sb can be will be rather different, but in uniform flow this SF and this SB, that is bed slope and the friction slope, remain same, because our depth is same in that portion where we are considering this as uniform flow. In that channel reach, this is constant, then velocity is same, and as such our energy and everything remains same. So, when we get this uniform flow, then our SB and SF is similar value, same value, and that is why many a time we write this formula, uniform flow formula, in terms of SB. We write this formula in terms of SB, that is, we write that V is equal to 1 by n r to the power 2 by 3, then we write SB to the power half. Why I am emphasizing this point? Well, why I am emphasizing this point? Because when we will be dealing with non-uniform flow, like that gradually varied flow, then also for some of the situation we approximate the small channel reach may be considered as uniform, though the entire flow reach is non-uniform, and in those portion we consider that uniform flow formula is valid. Well, but in that case we cannot use SB, we will have to use SF. So, that is why these sort of finer points we need to be careful. Well, then of course, we did discuss the factors affecting resistance parameters. So, resistance parameter N got affected by many factors, and that part also we did discuss in our last class, and we could see that although for a particular channel we may specify some definite value of Manning's N or maybe Sage's C, but in reality this sort of constant value is not possible, say with the change of depth. When the depth changes, this value changes, and then when suppose your bed characteristic is remaining same, bed material characteristic but suppose somehow the scouring is occurring in some portions, scouring is occurring in the channel reach, then your N value changes. And then similarly when siltation is there, it will be changing. If you are putting some breeze across the river, some obstructions are there, the N value will be changing. So, while doing this computation of uniform flow, we need to understand that though we specify some N value, in reality, or to be in more accurate, to have a more accurate calculation, we should know that this value will change, and when some changes are occurring, we need to change our N value accordingly. Well, then we started with computation of uniform flow, and that you can see what we mean, that it means computation of one of the flow parameters. One of the flow parameters means it may be depth, velocity, etc. using resistance flow formula, That is what we generally mean by computation of uniform flow. Well, now let me go to the next slide. Basic equation and its solution. Well, now by basic equation what we mean, that we know that suppose in a particular channel we know that how much discharge is coming. So, that Q is known to us, sometimes it may be known to us, and sometimes it may happen that we know the depth, we know some other parameter of the channel, and we need to compute how much discharge is actually flowing. So, it can be either way, and but from our very continuity equation what we know, that Q we can write as A V, Q we can write as area into velocity. Okay. Now, from that, say we can have an expression for this area and we can have the expression for this velocity from the any of the resistance flow equation, or say Manning's equation we can use. Well, right now I will be using Manning's equation for all these calculation, and of course you can have Sage's equation also. Now, say this V is nothing but that we can write as this is equal to area into This velocity we can write as, using Manning's equation we can write 1 by n, then r to the power 2 by 3 and SB to the power half. Again I am repeating that SB means it is because uniform flow we are talking about, that is why we are writing SB. Well, then what is R again? We can write that R is nothing but A by P. So, we can write 1 by A, then 1 by N, then A by P to the power 2 by 3 and SB to the power half. Well, now for a different section, this area and perimeter will be different. Well, let me take one section, say trapezoidal section. Okay, let me take one section. Let me consider that this is a trapezoidal section. Okay, and say my flow depth is this much. This depth, let it be y. And if it is uniform flow, we can write it as, of course, y n, that is normal depth. Well, for the time being, let it be y. And then for this section, say this is my bed width b. And then side slope we specify as z is to 1. That is for one height, this slope increases, the width increases by z. Okay. So, 1 is to z. Now, what will be the area of this section? That area of this section we can write that this is equal to nothing but b plus the top width. Now, what will be the top width? If I go like this, then from here to here again it is b, and then here to here it is z into y, and here also it is z into y. Okay. Well, now normally you will be finding that we write that area as this plus that, means b plus, say we can write b plus twice z y divided by 2 into the depth, or this we can write as b plus z y into y, and of course, writing normal depth we can write b plus z y n into y n if I write this as a normal depth. Well, but here though we use this equation for area, this is a simple equation of area from the any trapezoidal section, but we should remember one point. This equation we are writing when we are considering that our slope, that is the side slope, but this slope, do not confuse, there will be always in trapezoidal section there will be two slope we talk about. One is the side slope. So, that z what I am writing is, you can concentrate in the slide that z what is being written, this z is, we are talking about the side slope, but along the axis of the channel, the slope what is existing, that we call as a bed slope. So, that generally we express as b, and in this section this expression we are getting a is equal to b plus z y n into y n, considering that the side slope in both the side is equal, and otherwise if suppose there is a section where it is not symmetrical, maybe in one side it is like that and then it is going like that, and in another side it is like that, then suppose it is said as trapezoidal section, that is fine, but if you use this relation directly you will not be correct. You will have to use here a different z1 and here you have a z, small z value, say z is to 1. So, like that, if it is unsymmetrical section, then you will have to use a different formula. But the in why normally we do not discuss about this sort of section in open channel flow, because these channels suppose are man made in most of the case, or even if in some natural channel also, the side slope depends on, if it is natural, depending on the soil characteristic here, the erosion take place and somehow it get into a particular shape, and generally when the channel is flowing, the material of both side will be same, and that way we can have always say almost equal slope, equal side slope in both the channel. And say if it is man-made, definitely if we are giving lining, then for our convenience itself we can always make similar slope on the both side. And when that will also depend, basically suppose if it is a man-made canal, when we are cutting that channel, then also it will depend on the type of soil. Suppose if it is a very rocky terrain, and through the rocky terrain we are making a channel, then the side slope that we can make is almost vertical, because in a rock if we cut a vertical slope, there is no chance of failure. But if it is in a alluvial soil, and then if we make a vertical cut, it will definitely fail. So, there is no meaning in making that. So, we need to know that at what side slope, what inclination, that side will be stable, that there will not be slide. Okay, the side should be stable. So, there should not be any slide, and that way we decide that this should be our side slope. And normally when it is a man-made channel, it will be passing through a similar soil having on both sides, and that is why it is we go like this. Well, then what is our perimeter? Okay, this is what about the area. Then what is our perimeter? Say this perimeter we can write as perimeter, that we can write perimeter P. This is nothing but B plus say what this length is. This is say this is Z y and this is y. So, this inclined length will be root over say y square plus z square y square, and that sort of length we have two. Here is this one and here is this one. So, it is B plus this into 2. So, that will be our B plus twice then y square, bringing out of the root sign we can have y, and root over 1 plus z square. Well, and then again writing for uniform flow, we can write B plus twice y n. This is nothing but we are writing in a symbol that it is normal drift, root over 1 plus z square. Well, so like that we can have our expression for perimeter and area. Now, substituting these value in this equation, let us see what form we get, what form of equation we are getting. Well, Q is equal to 1 by n, then say a to the power 2 by 3 was there, and then there were another a here. So, we can write a to the power say, okay, let me write it here itself, 1 a b here and a by p to the power 2 by 3. Let me keep it in this form, and s b to the power half. So, just writing this expression, what we can have, a is equal to, just bringing it from b plus z y into y n. So, we can write b plus z y into y n, then 1 by n, then again we will be writing b plus z y n into y n. Then here as you can see, this is b plus twice y n root over 1 plus z square, b plus twice y n root over 1 plus z square, and then whole to the power 2 by 3, whole to the power 2 by 3. In fact, we could have written this to the power 5 by 3, covering this, bringing this here, and then it is s b to the power half. Well, now in this expression, let me put all y as y n. Let me put all y as y n, and then it is q. Q is equal to say 1 by n, and we can write like b plus z y n into y n, and then whole to the power we can make say 5 by 3, just multiplying this by that, and then here it will be b plus twice y n root over 1 plus z square and whole to the power 2 by 3 s p to the power half. Now, see in this expression, our suppose we know the discharge. So, given the discharge, if we want to calculate y n, then we have a problem. We have a problem means we cannot separate out y n, say because here we have say yn as a product with this part, but here we have yn with this one as well as with this one. So, we cannot bring out yn, we cannot separate yn as a single parameter here, and then say we cannot express from this equation in the form that yn is equal to function of those things directly, making it separate. We cannot write it like that, function of other things, other known parameters. So, knowing the q, knowing the b, and we cannot calculate the yn directly. So, that is the problem. But of course, suppose for a channel, if you know the normal depth, say yn is known, side slope z is known, bed width b is known, say everything are known. In that case, if you are asked to find out, and of course, Manning's n from the characteristic of the channel, that is also supposed to know, then you do not have any problem in finding the q. So, if someone asks you what is the discharge, you can directly put the yn value knowing that, and then you can calculate the discharge. But if you are asked that q is given, bed width is given, then your normal depth also this Manning's n is also given. In that case, to calculate yn directly you cannot calculate, and that is why it calls for some other method. Say many a time we can go for trial and error procedure or some other methods are there, and let us see what are the method that we follow for computing this uniform flow. So, because of this nature of this equation, we need to go for say trial and error method. You can concentrate into the slide that we need to go for trial and error method. So, what we mean by trial and error method? Very simple, that you put some value of yn in this equation, you can put some value of yn, and you can see, suppose your calculated discharge, your discharge you know that say it is 100, suppose 100 q max should be the discharge, and these parameters you know some value, and then say you put some value of yn and you check other value you are putting, then you check whether your discharge is becoming 100 q max or not. If not, suppose it has become 60 q max, okay, suppose it has become 60 q max, that means it is less than what it should be. That means what depth you are considering, or in the first trial what depth you are considering is say not sufficient. You need to increase this depth, you need to increase this depth. So, you are putting a second trial, which second trial value for normal depth which is higher than this one, and then with the higher value of yn again you are calculating, then suppose you are getting 90, then suppose you are calculating another third value, then suppose your value is you are getting 110, that means this time in the third trial what value of yn you have put is more than what it should be. Then again you reduce the value between the corresponding value of yn 2 what you are trying, then yn 3 what you are trying, you put the in between value and you try to arrive at the value of 100. So, this is what is trial and error procedure, but people nowadays no more go for this sort of trial and error by putting one by one value in hand calculation. It will be it is quite tedious, and then people use a very simple computer programming can be used for that purpose. Say in the computer program you can make to change this yn, and then you can see that when your value of yn, when your calculated value of q discharge is becoming equal to your your actual value of q, or maybe very minor difference, because getting exactly equal value is not possible. So, it is a very minor difference, then you stop the iteration. So, that sort of iteration we normally do in computer, and of course, some people prefer to use an Excel sheet. Well, what they do, this formula they write in a, you can write in a say Excel sheet, and then you can put different y value and directly the formula is written there. So, you are getting the q value for different y value, just you need to type y different value and you can check that whether your q value that you require is matching or not. So, that way either we go for computer programming or say some people use Excel sheet, that way we do go by trial and error method. Then sometimes we go for graphical procedure. I will be coming to this. Some sort of graphical procedure also we adopt. Then earlier, of course, some hydraulic chart or table were there, and now people hardly use these things. So, we will not be discussing about this particular method. And then we have fortunately some approximate solution also. Approximate solution means, as you could see that from the formula, from the shape of the formula, the direct exact solution you cannot get explicitly, but we have some method by which we can get some approximate solution for the normal depth. For particularly say for rectangular channel, we have some approximate solution which give almost correct result. Although the name is approximate solution, but it gives almost correct result. Similarly, in trapezoidal channel, we have some approximate formula which give correct result, but of course, it need finer correction by again trial and error. So, that way some formula are there that we will be discussing. Well, now, when we were saying that we need to go for trial and error procedure, or we need to go for all these different methods. Now, is it required for all sort of channel, or for some cases we may have direct solution of yn also? So, let us see that. Well, as we could write the formula, just let me start from this one, that is q is equal to say 1 by n, then b plus z yn into yn. So, we can write this b plus z yn into yn, this is to the power 5 by 3, and then we could see that b plus twice yn root over 1 plus z square. So, b plus twice yn root over 1 plus z square, and then this is to the power 2 by 3 sp to the power half. Well, now let me take the case of one point is clear, that if it is a trapezoidal channel, then we do not have direct solution, that point we have seen. Now, let us see if it is a rectangular channel. What will be the case? Okay. See, when it is rectangular channel, it means that this z value, that is the side slope z, is equal to 0. And then for that, if we write this expression, you can see that q is equal to 1 by n, then b into yn, simple, because we all know, and this will be 5 by 3, and what is the side slope, that is also simple, that b plus twice yn to the power 2 by 3 and sb to the power half. Now, the formula has took a very simple form, but here also you can see that you cannot separate this yn, because it is in product with b, and here it is again in one single term. So, you cannot bring it common, or that way you cannot have a expression that yn is equal to in terms of other parameter. Okay. Because of that, this formula, that means for rectangular channel also we cannot have a direct solution, as we cannot separate it out. So, what we mean, that this do not have direct solution. We can write that this do not have direct solution. Well, now let us see that for some other peculiar case, that means one can be wide rectangular channel. What can be wide rectangular channel? In wide rectangular channel, what we mean, that this is very wide, that we did discuss earlier also, that is B is very greater than the depth y. So, like big river, so this is y and this is B, and this B is very greater than y. Okay. For this sort of channel, the same formula, for it is basically rectangular formula. So, Q is equal to 1 by n, area is equal to B y n, side is equal to B plus twice y n, means perimeter is equal to, and this to the power 5 by 3 and this to the power 2 by 3, and then it is S B to the power half, area to the power 5 by 3. Now, in this, if it is wide rectangular channel, what we can write, that B plus twice y n, this twice y n being very small, twice y n being very small in comparison to B. So, how we can write B plus twice y n to the power something, that we can write as, that means this part we can neglect, twice y n we can neglect as compared to the value of B. So, we can write Q is equal to 1 by n, then B y n to the power 5 by 3, and this we can write as B. That means, this small distance or small length, this plus that, this plus that, that we can neglect, and we can write B to the power 2 by 3 as B to the power half. Now, you can see that y n can be separated out. This will become B to the power 5 by 3 divided by B to the power 2 by 3, and that we can definitely separate out, and y can separate out, that way we can get y directly. So, for wide rectangular channel, direct solution of y n exists, direct solution of y n exists. Means here, though we did discuss that trial and error procedure or graphical procedure or approximate formula, for all those whatever it may be, those procedure are not required for a wide rectangular channel, we can go directly. And then let us see another case, suppose triangular section, say triangular section. Well, by triangular section, here it is like that. Say our channel is triangular and we have Z, but here our B is equal to 0, or B is equal to 0. And if you put the same equation, Q is equal to 1 by n, A means say B plus Z y n into y n, you can write B plus Z y n into y n, that to the power 5 by 3, and this you can write as B plus twice y n root over 1 plus z square, the perimeter, and that to the power 2 by 3 as B to the power half. Now, what you can see here, that when your B becomes 0, when your B becomes 0 for triangular section, you will be having the expression like 1 by n, then it is Z y n, we can write Z y n square to the power 5 by 3, or let me write it like that, y n, let me remain it like that, and 5 by 3, and then this we can write as twice y n, this we can write as twice y n root over 1 plus z square whole to the power 2 by 3 as B to the power half. Well, now in this expression also it is interesting to see that y n, as I could say that this will become y n to the power say 10 by 3, and this will become y n to the power 2 by 3. Now, and these are in product term. So, what you can do, that you can just bring y n out of this equation, and then and you can make a, you can express this directly as y n in terms of some other variable, that is q b, and directly. So, that means as you can bring y n explicitly, b and z. So, as you can bring y n explicitly and you can solve for y n, here also when it is triangular section, you can have direct solution of you can have direct solution for yn normal drift. Well, that means that although we have all other procedure, different procedure that we just said about, but for wide rectangular channel and for triangular section, we do not require to go for all those method, or we can directly calculate for the value of normal drift. Well, having said that, now we can move. That means we know that we need to go for trial and error procedure or other graphical procedure only when our channel section is trapezoidal or rectangular or maybe parabolic, and other things can always be there, but I am talking about only the simple sections which we normally get. In that case, only these two sections, channel sections are coming. And now graphical procedure are there. Of course, one graphical procedure can people can say that when you need trial and error procedure, you can always have some y value, and then suppose in that expression you are having some y value, you put that y value, putting that y value we can calculate. Suppose for this y value we are arbitrarily putting, and this is the q value we are getting. We know that this is not our q, but putting some y value we are getting a q value. For another y value, suppose we are getting another q value. Again, let me try another y value, we are getting another q value. We should be careful that our required q is suppose somewhere here, our required q is suppose somewhere here, q required. Now, once we have points on the point larger than this required q and smaller than this required q, and we have few more points, and then we can just draw an approximate graph like this joining this point, and then we can see that for our required q what will be our y. That is of course a simple procedure. It is basically nothing but trial and error sort of things, that we are using different y, we are calculating q, and then we are plotting a graph. From that graph we are getting what will be our yn for that given q. Other things being same, that is your other section, sectional parameters are remaining same, b and these things are remaining same, b, j, these are remaining same. Well, but there are some graphical procedure that is which use a term called section factor, and then some graphs are plot. Of course, now as I told that graphical procedures are not that much in use, because we have computer in our hand, and so with simple calculator also using approximate solution we can solve it. And then again some programmable computers are also there, you can directly calculate there. So graphical procedures are losing its importance, but still I will be discussing this this graphical procedure which use section factor, because it has some important factors and that we need to discuss. Okay. Now, what is section factor? Okay. Now, say let me write first q is equal to say 1 by n, then we can write it in a different form, that a r to the power 2 by 3 means including this area into velocity, a r to the power 2 by 3 and to the power half. Okay. This charge is equal to area into velocity. Velocity means this part and this 1 by n, and this part basically is the coming from Manning's equation, and this area into velocity. So, it is. So, this we can write as, out of this actually 1 by n a r to the power 2 by 3. Now, for a given section, this component SB I am writing here separately is called convex of the section. This part is called convex of the section, that will be coming later again. Convex, this is called convex K, generally K is the notation that is used for that purpose. Well, now here in this conveyance there are factors, suppose area and then hydraulic radius. Hydraulic radius is nothing but again area by perimeter. So, these factors are basically related to the sectional size of the open channel, and then this n, it is not related to the sectional size of the, or not related to the size of the channel section, rather it is related to the roughness characteristic of the channel, and of course, some other parameter what we did discuss earlier that influences the n value, but definitely not the sectional size of the channel. So, we can again separate out from here, that is q is equal to say 1 by n, then a r to the power 2 by 3 this, and then s b to the power half. This we call as a section factor, this we call as a section factor. Okay. So, for a particular channel, this section factor for different depth, given the depth, suppose whatever the section may be, for whatever the section may be, if we do not consider the other things, then given the depth we can find area, we can find radius, then we can find the hydraulic radius r, and then we can find out what the section factor is. For different depth we will be getting different section factor. Okay. And for section factor generally a symbol z is used. Of course, do not confuse this with the side slope z, this notation is used, a capital Z is used for section factor. And then we can have, that is well, in the, we can write it as q is equal to 1 by n, then a r to the power 2 by 3 I am writing as section factor z, and then s b to the power half. So, from that what can be written, this is equal to say section factor z, that we can write as q n and s b to the power half. Well, what it mean that though section factor z is a parameter which is related to the sectional dimension of the channel, and of course, sectional dimension of the flow section rather, but this we can get indirectly as when we know a q, discharge is known, then say meanings roughness coefficient is known, bed slope is known, then by this expression also we can find out what is the section factor j. Well, now using this advantage, what was done, some graphs were plotted, and then that graphs was basically made non-dimensional graph. Well, that I will be coming, and then from that graph we could calculate the uniform flow depth. So, okay, let me just draw the graph. This was plotted in log scale, and then so our value will be like that, say it is 0.01. On the y axis we were plotting, we can plot say non-dimensional depth, means this is say y is the depth and then y n is the depth suppose, and then for y if we divide it by b, if we divide it by the b, or let me write it as b, b means the bed width of the channel, then this we can call as a non-dimensional depth, this we can call as a non-dimensional depth. And then this value suppose 0.1, then we are writing 1, and then we are writing say 10. So, it is 0.1, 1 and 10, that way we are dividing it, and here it is starting from in this side we are writing the section factor, that is a r to the power 2 by 3, a r to the power 2 by 3, and this in fact has the dimension, say area will be having a dimension of L to the power 2, that means L square, length square is the dimension. R hydraulic radius, so its dimension is also length, so it will be length to the power 2 by 3. So, what is its dimension, say we can write L to the power 2 by 3 for this r, that is length parameter, and then it is L square. So, this will become L to the power, then it is 8 by 3. So, its dimension is basically length to the power 8 by 3. So, to make it non-dimensional, if we divide it by again b to the power 8 by 3, this become non-dimensional. Okay. Now, so on this side we are putting a r to the power 2 by 3, that is section factor divided by b to the power 8 by 3. Well, and this start from 0.0001, then it is becoming 0.001, then it is 0.01, 0.1, then it is 1, and then it is becoming 10. This is becoming 10. Well, so this within this range we can plot this value. Well, now, okay, let me draw some line as a guiding. So, this b, it is divided by b when it is a, I mean b to the power 8 by 3, the section factor we are dividing by b to the power 8 by 3 when it is a trapezoidal section like this one. But this graph, that is graph of section factor, that was also plotted for circular section, and in that case we do not have any b. So, in that case for circular section we can plot here y n by d, that is the diameter of the circular section. Well, this d 0 normally is used, and then here also it is plotted either this or say a r to the power 2 by 3 divided by d 0 to the power 8 by 3. What is d? When we take a circular section, then this diameter is considered as d 0. Okay. Well, now just putting this value, if a graph is plotted, then for circular section what we get, the graph is like this. For circular section we are getting a graph like this. It goes like this, and then just after crossing this value it is coming like that. Now, why I am plotting this? Just to emphasize what this portion mean. Okay, I will come back to that. And for trapezoidal section, trapezoidal means if we make z is equal to 0, then it become rectangular. So, for rectangular section also it was plotted, and for that we can write that for rectangular channel this graph goes like that one. It goes like that. And then this is say for z equal to 0. Let me draw it properly. This is going like z equal to 0, say z equal to 0. Then with the increase of z value, say z equal to 0.5, we are getting it like this. Then suppose z is increasing, then it is going like this, z equal to 1. Then this part it is becoming narrow, this is not changing that much, but here it is changing, z equal to 1.5, and z equal to it is further increasing, z equal to 2, like that with the increase of z value, that means the side slope z. Oh well, do not confuse this z and that z, I should have used a different symbol here. Well, here in this graph, say for section factor let me put is z1, okay, and this z is representing side slope. Well, so this z is side slope, and section factor I can write as z1. Here of course I am not writing any symbol for section factor, I am writing a r to the power 2 by 3 directly. Well, so that way we can have this curve. Now, suppose a discharge is given to you, and that roughness parameter, that is the resistance parameter, roughness parameter that we call, that n is known to us, and then slope, bed slope is known to us. That means these three, you can concentrate into the slide, these three parameter, that is q, n and this SB, these three parameters are known to us. Then we can calculate what will be the Z1 section factor, what will be the Z1 value of that particular flow. And for that Z1 value, now we know that what is the side slope. Suppose it is rectangular channel, then what we will do, we will first see in this graph, then we know the b value. So, we can have b z divided by z1 to the power 2 by 3 divided by this b. So, that value we will be getting here. Suppose this is this much. For our particular problem, it is this much. If it is rectangular, we will be going to this particular graph, and then we are getting what, that y n by b value. We are getting y n by b value. Now, we know the b, so we can calculate what the y n is. Once we know the y n by b value from this graph, then we can calculate what the y n value is. So, that way, knowing these things, we can calculate the normal depth. If your z is suppose 1 or z is 1.5, then from the same point you will be going to the another curve, the corresponding curve, and you see what the y n by b value. Now, the problem, if your z value, suppose it is a circular channel, okay. Suppose it is a circular channel. Now, if it is a circular channel and say your z value has come up to this much, z1 value, I am talking about section factor value, then you are coming to the curve of circular. If you are here, there is no problem. If it is a circular curve, you are going there and you are finding a value. If you are here, you are going to this curve and you are getting a value here. So, for this point there is no problem. But when you are going to a very higher value of z, that means your q value is increasing and then your z value is increasing, z1 value, I mean the section factor value is increasing, then you are coming to a point at this portion, and the non-dimensional section factor, this divided by b to the power 8 by 3, and then your problem arises, because in this curve you have 2 point, okay. Once we have 2 point here, that means for this z we can have this value as well as we can have this value. For this value you are getting one normal depth, one y n by b value, non-dimensional depth first, and then for this value you are having another non-dimensional depth. Both this value will give you one a different normal depth. Of course, this depth, difference in this depth are very small, but in reality also in circular channel, that is why we say that for higher discharge we can have 2 normal depth. Probably you remember when we started uniform flow, computation, rather we were discussing about uniform flow, normal depth, then we were discussing that there is an exceptional case in circular channel. In other channel we can get, for a given discharge we can get one uniform flow depth, that is for a given section there can be one normal depth only for a given discharge. For a given slope, given discharge, given section, we can have one normal depth, one depth where the uniform flow can occur, and that we call as a normal depth. But for circular section, when it is just about to touch the surface, top of this is about to become complete, so when z value is very high, then we can have 2 cases of uniform flow depth. Computationally we could see that. And of course, one thing is very clear, that if it is a circular channel, and suppose the surface is closed, if it exceed a particular limit, that means when there is no suppose no space on the top, when it is completely full, then the flow itself will have to deal as a different type of flow. Then it will no more be a open channel flow, and rather it will become a pipe flow concept, and then we will have to think about other theories, other relation, and that way that is another issue. But here when till it is open channel flow, it is not completely covered, pressure is there, we can have 2 normal depth. Well, about this uniform flow formula, whatever it is, maybe Sage's formula, Manning's formula, all these, then say let me write the Manning's formula. It is V is equal to 1 by n r to the power 2 by 3, then s to the power half, SB or SF, whatever it is. Well, now here we are using the value of n, and then n value is given normally as a just digital value. Digital value, I mean that a numerical value is given. Say for a smooth channel, very smooth channel, we can say call n is equal to, it can be suppose 0.01. For a rough channel, n can be equal to say 0.025. Then if it is further suppose very rough bed and side, then we can write it as 0.035, like that. It can keep on increasing. I mean, just this is I am putting some arbitrary value without mentioning what the type of channel are. But now when we are using this value, we are not putting any unit for this n. We are not putting any unit for this n. Means suppose when we write about velocity, we write velocity is equal to this much meter per second, depth suppose this much meter, but here we are just writing some value. So, we will have to be very much careful in using this formula. That is, in fact, this n is not a non-dimensional term, it has some dimension, though we are not writing the unit on the side. And that is why when we are using this, we are already knowing that this we are using when for a particular value of b or particular unit of b. That means, b is suppose in meter per second, r is in meter, and s of course, this bed slope is not having any unit. So, so that we are knowing the unit of r and v. If it is in meter and second, then we can say that n value are like this. If this v and r value are in suppose feet and second, then this our n value will be different, the n value will be different. So, we need to know that the dimension has a role to play in this sort of equation. And okay, if we say what will be the dimension of n, that also we can find out in Excel. Say n we can write as n is equal to, we can write r to the power 2 by 3 s to the power half divided by say v. Now, if I write the length dimension as L and say time dimension as T, this is say length dimension and this is the time dimension, then we can write n is equal to, and I mean not equal to, basically we are talking about the dimension, what is the dimension of n, r, that we can write length to the power 2 by 3, and then s, whether it is bed slope or whether it is friction slope, this is not having any dimension as we know, and then v, velocity, will be having the dimension of meter per second. So, it is length by t. So, L t to the power minus 1 we can write, and that actually what will be the dimension, that will be L to the power 2 by 3 minus L to the power 2 by 3 minus 1, and then it is t we can write. So, this is equal to, we can write that L to the power minus 1 by 3 and t. So, this will be the dimension of n. Well, now with using this dimension and considering this dimension also, we can develop a equation of the uniform flow, what we have already written for trapezoidal channel. Then the same equation we can write in a different form, that we call as a non-dimensional equation of open channel flow. And using these then there will be coming a non-dimensional discharge, and of course, we will be talking about a non-dimensional depth like y by b. So, using that we can have a relation, and taking advantage of this relation we can have some formula that we initially discussed, that approximate formula of computing normal depth, and that of course we will be discussing in the next class. Well, let us get ready for the next class, so that we can start with a fresh mind to see how this approximate formula can be used, and how we can using this, what is the advantage of using this approximate formula. Thank you very much.